So today we're very happy to have with us, at least electronically, Alessandro Lazaric from Meta AI, where he's team lead of the reinforcement learning team at FAIR Paris. And he's going to tell us about his work in exploration in reinforcement learning. Thank you, Alessandro. All yours.
Thank you so much for having me. Apologies again for not being there in person. Unfortunately, in France, there's going to be a strike tomorrow, and this disrupted a little bit my trip plans. I will definitely stay, much longer than the talk. So definitely happy to connect with whoever wants to have a chat after this. I'm happy to continue and stay longer. So let me just double check everything is fine on the video side, so you can see my slides, right? Okay, hopefully yes. So the talk is understanding unsupervised exploration for call-based RL. So the understanding part is really because the talk will be not giving a lot of algorithms, a lot of experiments, but it's really more trying to understand what it actually means, or one possible instance of what unsupervised exploration might mean, and what are the intricacies of this objective. So just let me start with general context. We know that there are a lot of problems out there: robotics, recommender systems, portfolio management, games, autonomous cars, that can be to some extent formalized as data-driven sequential decision-making under uncertainty. And this is where RL is one of the tools that we could use to tackle these problems. So somehow RL is a broad applicability, at least on paper, in terms of the formalism. But when we actually try to do it in practice, it struggles with very high simple inefficiency and several other limitations. So it's true that, for instance, we can find what is the optimal strategy for playing Atari Breakout, but this requires millions of rewarded interactions before being able to do that. And once that is done, if we change the game, well, we cannot really do much. Similarly, for instance, I don't know, if we play Pac-Man, millions of rewarded interactions, reinforcement learning is well equipped to give you a Pac-Man expert, but if we change a little bit the game, we're not really able to generalize much more than that. So generally speaking, there is a trend in reinforcement learning. Definitely, we are not the first to identify this trend of taking a shift in how we approach reinforcement learning by taking a unsupervised, self-supervised approach to the problem, where we are given the possibility of interacting with a domain, an environment, in a way which might not even be rewarded at all, with the objective not really of solving a task at that point, but defining and finding enough expertise about this domain so that at downstream time, we will be able to solve specific tasks specified maybe through language, maybe through a reward, through demonstrations, in a way which is either zero shot or few shot. So in this example, let's say that we have a very simple robotic arm and a table where we can displace objects. And we just want to understand what is the dynamics of the arm and trying to understand how to interact with the objects. And eventually, maybe we are given a specific task, which is push the block to the right location, and we are able to execute this task very effectively. So in the end, we obtain an expert, which is more general than solving just one task, which can be controlled through some prompts. Now, this is a very complex and ambitious objective somehow. What I'm going to focus through this talk is the unsupervised exploration of these picture somehow. So how do we actually interact with an environment when we don't have any reward, and what are the sensible objectives that we could set during this phase? And at downstream, I will narrow down things a lot to just goal-based RL. So downstream time, I will be given a specific goal, and I will try to execute a good policy to accomplish that task. So overall, basically, we are trying to do is to autonomously explore and learn the ability to reach a set of goal states of interest as soon as they are specified at test time. Now, let me give a very qualitative and illustration of in the long term what we could hope to get. This is I want to give credit to both the owner of this video, Francis Vachon, and also Cédric Collin, who gave a talk a while ago in our lab, who showed us this video, which I find quite fun. So we see a baby just exploring, right? Exploring this environment. I think it's basically 2 hours compressed in a couple of minutes, where it's setting goals, maybe moving to a specific location, maybe grabbing a specific object, or turning a toy in a certain way, or combining things together in a totally autonomous way, right? So there's no specific objective provided in form of a goal or in form of a reward function. And this happens in a totally intrinsically motivated way. And the thing which is really interesting here is that there are certain actions, certain things that require a careful expansion of the things that the baby is doing. Before knowing how to move to an extreme of a room, the baby needs first to explore the things that are close to it, as well as before manipulating and combining objects in a very sophisticated way, you will first learn to, manipulate things in isolation, and only later to build on this skill to develop more complex abilities. And all of this, again, it happens in an incremental way and in a totally unsupervised fashion. The thing which misses in this video is what I was saying at downstream, where at a certain point, if the baby, let's say, would be requested to maybe go and grab that toy for me and bring it to me, at that point, the baby will leverage what they learn across this explorative phase to accomplish that task that maybe the parent provides them. So this is, the long-term kind of vision that, eventually we would like to generate autonomous explorative agents that are able to behave like this. So let me give a one-slide summary. Disclaimer, I usually go very long with my talks, so I have to cut things. So I took the habit to, just summarize things in one slide. And at least, I know that I can deliver the basic message early on. So there are 2 things that we learn in this line of research. The first one is that efficient, unsupervised exploration of a completely unknown environment to learn goal-based skills, it is possible in a certain sense, in a way which is efficient, simple, efficient, but it may be hard. There are some certain situations where this might actually take a long time and not be that efficient. So there is an alternative way of doing exploration, which is more incremental, which is more efficient, for which we can provide much better efficiency guarantees, but in the end, it might filter out many goals that we might or might not consider as interesting. And this is where somehow the designer comes into the picture. So either we target very general and possibly complex goals, and then we have very hard exploration in the worst case, or we are more incremental in the way we want to discover things. And this leads to more efficient algorithms, but possibly restricting what we are able to do at downstream in a significant way. What we're missing here is extensive benchmark evaluations and empirical validations. I will come back to these towards the end of the talk, and also how to blend together more efficiently unsupervised exploration and representation learning at the same time. And again, I will come back to this towards the end. So I have my slides in front of me. Feel free to jump in, mic on, and ask questions at any point in time. I will try to pose anyway through the talk, so that you can jump in and ask any question. So first of all, let me thank great collaborators that have been working on these topics together with me, Jean Tarbriesh, Michal, Matteo, Omar, and Pierre that have been contributing a lot to a lot of the things that I will be talking about today. Outline. Let me first formalize what it means to do a supervised exploration in goal-based at high level, and then I will critically introduce the concept of controllable states and incrementally controllable states will that will shift from the first.
Alessandro? Yeah, there is
Hello?
a question here in the audience.
Sorry, so my question is why incremental learning filters out some goals? Can you not have or design guided incremental learning where you predefine your goals?
Oh, so what you will see in a couple of slides, one thing that I really don't want to do is to predefine goals. So I want this to be really full and supervised to some extent. And so I want the process so I want to prescribe goals of interest, but without really explicitly telling the agent what these are, because otherwise it means that as a designer, I already know what I wanted downstream, and it would be maybe a little bit too much prior knowledge. And the incremental aspect, you will see it's a little bit subtle, but if we want to have really an agent which is very considerate in how it explores things. And it says, I want to consolidate things. And then when I'm confident about something, I take on more difficult goals and more difficult goals. Then it might actually filter out some goals because they're not really amenable to this layered or curriculum that the algorithm would end up doing. But I will, try to go much deeper on this in the technical part and on the third bullet point here. Okay, so unsupervised exploration for goal-based RL. Goal-based reinforcement learning is very interesting because it encompasses large set of practical scenarios that can range from navigation to robotics to games. And so it seems like it's a interesting enough setting to consider when we define unsupervised exploration. Again, there are a lot of other problems that are not goal-based, but I think it's broad enough to have its own interest. Let me formalize it very quickly, not too much notation, hopefully here. An MDP standard definition. So there is a state space S. Here, there is one specific state that is the initial state from which we want the agent to learn how to reach goals. So there is a specific state. We could generalize it to a set of initial states, but for simplicity, let's say that there is an initial configuration S0. And then there is a specific goal, which we denote as G, which is the goal. There is a set of actions that the agent can perform. There is some dynamics that prescribe how the environment evolves from a state to another one, given the action, and transitions can be stochastic. And then here, just keep in mind through all the talk, I will talk about costs instead of rewards, just because it's easier when we define the problem of reaching goals. And so basically we suffer a cost of 1 at every step, except when we reach the goal. And so the overall objective of the agent will be to try to find really the shortest path. So the minimum amount of steps to reach the goal. So we want to minimize cost. And so smaller is better with respect to maximizing rewards as usually in RL. I will use pi to denote a policy. We can stick to deterministic policies. So it's a mapping between states to actions. And here I will also use tau pi as RO S prime as the time it takes to move from S to S prime by following the actions prescribed by policy pi. This can be random because transitions might be random. And so in general, we will be focusing on the value function, which is the expected hitting time. So I will use the standard notation V pi, but we'll denote S ROS prime to really explain that it's the average time number of steps that takes to move from S to S prime by following pi. And usually, again, we will be focusing on how long it takes to move from S0 to G. Let's extend it just a little bit to multiple goals. So I will denote usually with a curly G a subset of the states, which are the goals. And at that point, I will also expand the notion of policy from just state to actions, from state and a prescribed goal to the action that I would like to take. So I will call it goal-based policy. It is standard in goal-based RL literature. Okay, so what are the objectives? What are the interesting or relevant and super guide goals? So one thing is to say, hey, you know what? You're in an environment. I want you to learn how to reach all states, right? So I at test time, you might be asked to reach any possible state. Well, this is already not only it might be very difficult because there are states that are very, very far, they're very difficult to discover and so on and so forth. But it also has a huge assumption, which usually it's not verified in practice, which at design time, I do know what states make sense, what states are actually even reachable. Imagine the standard, I don't know, mountain car environment. If I take the Cartesian product between position and velocity, actually, if I don't know anything about mountain cars, I might not even know what is the range of the variables and whether the whole Cartesian product is actually reachable. And so if I ask to the agent, go to a specific configuration, which is not even reachable, I might actually create a lot of problems to the agent. And so usually it requires prior knowledge of the valley states, which we don't have that often. Then we might say, okay, not all states, but just some very carefully chosen states that I think they're of interest. Again, this means that we are not that unsupervised in the end, right? I mean, basically, we are prescribing what are the goals that we care about at test time. So it requires prior knowledge, and it also, the risk is to have limited generalization. If at downstream time, I might change my mind and I say, oh, maybe there are other states of interest that I didn't list at the beginning. So the way we are going to do it is slightly different. It says, just develop some expertise around your initial state. So I will define a sort of radius of competence, if you want, which is, I would like at the end of your unsupervised exploration phase to be able to reach all the goals that are within a certain distance of your initial state. Now, at design time, I have no idea which states they are. I'm just telling you, explore this room, and I don't even know how big is this room. I don't know. I just tell you, within a certain distance. This doesn't require any prior knowledge about the environment. It seems kind of still a natural and meaningful objective for the goal. It enables very easily curriculum learning because at the beginning, I might tell you, reach states that are 5 steps away, then say, okay, now once you're done with that, go to 10 steps away, then 15, 20, 50, and so on and so forth. So it enables some form of curriculum learning and compositionality. The tricky part is that then this set is totally unknown to the agent. So the agent now is charged with an additional question, which is not only what are the good policies to reach those goals, but what are these goals, right? And we give the agent very little prior knowledge about that. So let me try to illustrate, with one example, which is a little bit far-fetched, but it's illustrative and it might, help in driving some of the concepts that I'm going to cover later. So let's say that you're in this type of maze environment. You're in the initial state is the one in green. And you have, let's say, nearly deterministic dynamics in general, move left, move right, up and down. But there is a specific region in which is the bottom one in this environment, which is if you're familiar with that concept, is the infamous noisy TV. So imagine that it's a region where the walls are projecting random noise. So whenever I go through that, my input, let's say the image of the camera, is very noisy, right? So it's something that every time I pass through those regions, it changes because it's just projecting white noise, let's say. So let's say that we have this type of environment. Again, the more maybe sensible framing of these is you might have, I don't know, certain part of the state space where, I don't know, it's dark, so your camera is more noisy, it's less reliable. And on the other hand, maybe the upper part of your maze, of your environment, there's a lot of light, your sensors are functioning very well. Okay, now let's say that I tell you, find all the states that are reachable from the green one within 5 steps. So states that we might expect our algorithm to discover and find good policies to reach are, for instance, this one, because with just 5 steps, I can get there confidently, repeatedly. So good. It might be this one. So just move straight right from left to right to reach this red goal, and it's not that difficult. You just need to move straight. But then even specific configurations of this noisy TV are actually reachable in just a couple of states, right? I mean, I can reach that region of the space where I observe this noisy TV very easily. It's not a complicated state to reach. So now the underlying question is, are all these states equally difficult to discover and to learn a good policy for? And what are the best algorithmic strategies to overall discover and control these states? These are kind of the 2 questions that hopefully I will address moving forward. And the first step now is to really go into unsupervised exploration for controllable states, which I will define in a second. Let me pause just 10 seconds here in case there is any question about this example or what I've said so far. And again, feel free to just unmute and for those that are on Zoom call. Okay, so then let's move on, and let's define first the notion of controllable state, which is a very first filter that we would like to put, which is really important to make our problem to some extent well posed. So I will semantically, this is totally arbitrary choice of words if you want, I will distinguish between reachable state and a controllable state. So let's say that you start from the green state, you move up, and then you just roll a dice, completely random transition, and you end up in any of those states that are represented there. So then let's pick one. Let's say the one in red. That one is totally reachable, right? There is, if I move up, there is some probability that I will reach it in just 1 step, right? So it is reachable in the sense that there is a non-zero probability to reach it. But then if I wonder whether this is actually something that I can control, and by controlling here, what I mean is, can I confidently generate that outcome? Can I really decide to go to that state? Well, the answer is no, because I ended up in that state just because randomness, but I cannot really control that outcome. On the other hand, if we look at on the right, I might still suffer a little bit from noise. Like, first step, it's random. So I do one action, but the outcome of the action, it might be to fall into the left, up, or right. But now there is a very clean and reliable path in any of these 3 events to reach the red goal. So in this case, I can confidently say that, sure, there is a little bit of uncertainty about how many steps it might take to reach that goal. But overall, I'm confident that if I follow that policy, I will end up there. So it's really, the difference between saying, I want to go from my place to the office. Well, sure, I might not know, I might miss the bus, or traffic might be heavy that day, might rain. There might be some stochastic events that define how long it takes, but on average, I'm gonna be there. I'm gonna get there. I'm reviewing catastrophic events. On the other hand, if you ask me, very, very specific things like, having the bus arriving perfectly at that minute and so on and so forth, sure, I can go downstairs and wait for the bus. So this is the controllable part of my actions, but I cannot really determine the specific outcome. So sure, that specific state might verify itself, but I cannot control it. So this is exactly what happens with the noisy TV. So we can reach any of the configurations of this noisy TV, but we cannot really reproduce it confidently in a finite time, right? There is some probability, but not that much. And so coming back to this example, the first goal on the left and the one on the right, those are good because, there is confidently a way to reach them. But the specific states that I observe when I pass through the noisy TV region, there are not really things that I can control. And so the first thing that we have to be mindful about, and again, the agent doesn't know it in advance, is that along our exploration, we might see a lot of things, but it's really crucial not to be driven by things that did happen, but by luck or by just random transitions, and things that I can confidently reproduce. So we will first need to have algorithms that are robust and not being tricked in spending a lot of time say, oh, I observed that state, so it means that it's controllable. Let me try to find what is the good policy to do it. And maybe it is controllable, maybe it is not controllable, and the agent has to find and be discriminative in this sense to avoid wasting an incredible amount of time of trying to really reproduce that specific configuration, say for the noisy TV. So let me move in that sense to unsupervised multi-goal exploration. We are introducing one assumption, which is we can reset. This is more technical. We don't want to be lost in catastrophic events forever. So we want to be able to reset from time to time to the initial state to be able to learn how to improve things. We will be provided with the goal radius. So that radius of components that I was mentioning, some accuracy level that you will see in a second, what is its role. And then the set of goals, I will define it as the set of states for which there exists a policy that can reach that goal on average in less than L steps. And this is, the tricky part. I don't know what is the policy, but additionally, I don't even know what is this goal set is at the beginning of my exploration phase. And what I would hope for is to devise an algorithm that interacts with the environment, say for tau steps, and at a certain point says, I'm done, right? I will return a goal-based policy that I'm confidently, it accurately control a set of goal states, let's call it X, that it should match, hopefully, as closely as possible, this GL state. So this is what I'm asking now to my algorithm. Interact for how long you need, then you raise a flag, say, I'm done, and by the time you're done, you give me good policies to reach the states that implicitly I did prescribe to you, which might appear then a downstream task. So let's formalize this. This is a little bit of a scary and a big slide, but it's just to formalize what I just said. So we'll say that an algorithm, successfully solved this problem if a certain set of conditions is verified. Well, the first thing is that it stops after tau steps, which should not be too big. So it should be polynomial in the number of states, number of actions, the radius, how far things should be, the accuracy that I want to get, so 1/epsilon, and this kind of stuff. Okay, so this is easy. I can stop whenever I want, so I will try to stop as early as possible. But now, what are the prescriptive questions? Well, the first thing is that I want you to return near optimal goal-based policy. So I want you eventually to return good policies. And I want you to do it with an accuracy epsilon with high probability, right? This probability of being bigger 1 minus L, that just means that, the algorithm is robust, it's reliable. And because, we want to make things difficult, I don't want you to give me policies to reach goals that you like. No, I want you to reach goals well, accurately, on a set of states, which, leave it or take, is the one that I prescribed at the beginning, which are the L controllable states. Maybe you can go a little bit farther than that. So maybe you don't, recover just GL, you recover GL plus epsilon. So those that are not just L controllable, but L plus epsilon controllable, fair enough. But I don't want you to, just cover the whole state space or crazy things like this. So I want you to be laser focused. Now, what are the algorithmic, structure that we are following to try to solve and approach this problem? So, we've been a little bit fun here. There is BIOL, which is bootstrap your own latents. Here we call it SIOG, set your own goals. And this is, just trying to formalize things that have been around for many, many years in RL, which are, how to prioritize goals, how to explore an environment in an intrinsically motivated way. So this is, takes a lot of inspiration from those things, but tries also to formalize it and provides a little bit more guarantees. But the general scheme is the agent should define a prioritization scheme, define what goal I'm trying to reach next, and then try to execute the policy that I learned so far to reach that goal, adding a little bit of exploration to it. So this is the reason why I call it an exploratory version of it. Collect more data, more experience, try to improve, thanks to this experience, the policy that I learned, and then trying to devise a stopping rule, which says, am I good enough on the things that I believe are relevant? Then I stop. Otherwise, let me pick another goal and so on and so forth. And again, you see here the risk, right? So if I get the first step, for instance, wrong, and I stubbornly try to get right, finding a good policy to reach a specific configuration of the noisy TV, then I'm doomed, right? I would keep trying and trying and trying and failing because, well, it's actually not L controllable in the first place. So we have to be very careful here. So we try to implement, this general scheme into a specific algorithm, which we call ADA goal. So in the paper that is mentioned here at the bottom, we have basically 3 versions. We have the theoretical version for tabular MDPs, a theoretical version for linear MDPs, and then a more scalable deep RL amenable version of it, which I will mention at the end, which you can use with neural networks and stuff, which we used in very touch example. So what are the 2 ingredients? And here, really, I don't want to enter in too much into the technicalities of how we instantiate these in these three settings, tabular, linear MDPs, and deep RL, because I want just to deliver first the general context. The concept is 2 ingredients. The first one is there is an optimal policy, let's say, to move from initial state of 0 to G, which has a value, so average number of steps, which is V star. Now, what I would like the algorithm to maintain is an optimistic estimate of that. Optimistic, again, remember, the lower the better, which means that I will have an estimated decay of G, which is upper bounded by V star. So it's smaller. I'm hallucinating a better word where instead of V star steps, maybe I guess that it will take less than that to reach the goal. So I want to first keep an optimistic estimate of that. And then a subtle but very important notion of uncertainty. So here is basically, let's call it performance loss to some extent. So if I, at iteration K, I have a certain policy pi K that I would be executing if asked now, if I stop now, pi K is the policy that I would be executing, the goal-based policy to go from S0 to G. It has a certain value, maybe good, maybe not. And hopefully I would like this to be not too bad with respect to V star, or to make it more algorithmically amenable with respect to our optimistic estimate. Now, notice that VPyK is something that we don't know, right? I mean, unless we do rollouts or we try to estimate it, we don't want to know that. What we want to keep is an estimate of how much my policy is not optimal, right? So VPyK is how much my policy is actually taking to reach G. DK is a sort of a guess about how long it should take optimally. And this EK is an estimate of how much I'm not optimal, right? How much performance loss I'm currently suffering. Now, the key point is that if you have this DK and if you have this EK, and we have ways to formally implement them in the tabular linear MDPs and a more scalable version in DeepRL, if we have these two ingredients, then we are good to go to solve the problem. And the way to do it is to implement out those steps following using these ingredients. First one is to say how to select relevant goals. I will select the goals that have the estimated suboptimality in terms of what I would be doing now and how bad it could be with respect to the optimal thing I should be doing to reach G. The one which is the worst performance loss, it should be the one which is prioritized. Now, let me stress here that it's very different from saying that reaching that goal is difficult. What I'm saying is that the way I know how to reach that goal is probably not very good compared to how I should be doing it. It's not an evaluation whether that goal is far, whether it's close. So the illustration I have here on the right is really saying I might have a very small EK, so this estimate, for goals that are very close or are very far, right? So I might be very confident that those goals are far and I have a very good way to reach them. In that case, I don't want to prioritize this. There's nothing more to learn there. So we really want to focus on uncertainty and not difficulty. Then how to execute an exploratory policy and improve over it. There are plenty of algorithms in the literature about how to do shortest path exploration, not really, diving into that. And then the stopping criterion is relatively simple. It says, if I reach enough confidence such that all my EK for all goals is below epsilon, then I stop. But again, I have to be mindful about which goals. And here is where the optimistic estimate comes into the picture. I want to be accurate enough so that E to be smaller than epsilon for all goals that optimistically I could reach within L steps. So this is a way to, again, limit my exploration to things that are hopefully within that radius. And then what I'm doing is returning that set of states and returning the associated policies. And hopefully I've done a good job. So simple complexity bounds, again, in the tabular case, we have everything, it's very rigorous and theoretically grounded. And we can tell you that you're able to solve the problem. So finding the good set, giving me epsilon accurate policies after these many interactions in the worst case. So this depends on number of states, number of actions, the accuracy at the denominator epsilon squared, and the radius L cube. I'm not going to dive much deeper into this because I will come back to it later. But just to say, okay, the algorithm and its theoretical instantiation is sound. We have guarantees for it. But let me try to get a sense about whether it works and maybe in the interest of time I will skip this toyish illustration and rather move to its very trivial DeepRL implementation, which turns out actually it has a lot of overlap with value disagreement learning by Zhang in 2020. So the way we are doing is you have multiple estimations of this of the quality of your policy pi for moving your goal-based policy of moving from S0 to a specific goal G, which is in your replay buffer. And instead of having just one evaluation of that, we have multiple evaluations which are trained, basically multiple neural networks trained using randomized subsets of your replay buffer. And we use the standard deviation trivially to evaluate the uncertainty. So it's really a sort of bootstrap version of theoretical confidence interval driven estimations of your uncertainty. And then again, the rest of the scheme is the same, like we're prioritizing targeting goals where this EKG is large, gain goals that appeared in your replay buffer, and eventually we just return the policies that we learned. So let me give this again, very toyish illustration, but I think it provides a little bit of the flavor of what we are trying to achieve here. So let's say that I introduce some prior knowledge. So I have this problem of moving, the black block to the red dot, and I know in advance, design time, that at test time you will always only be given goals that are on the table, right? A prior knowledge. Then, well, honestly, if you have this prior knowledge, whether you do goal prioritization, all those Mars things that I mentioned, or you just, build a replay buffer by, a bit of exploration and do uniform prioritization over goals which appear in your replay buffer, which are on the table, then you're good to go. So you see that on the right, I have a couple of plots for a couple of specific instances of downstream goals, where success rate, whether you use our algorithm or uniform allocation over the replay buffer, it's exactly the same performance. No real significant difference. But now let's imagine that at train time, I have no idea whether you will be asked to reach goals which are on the table or not, and I let you observe goals that are, for instance, beyond the table. So now this is a little bit, in flavor those non-controllable things, in the sense that, sure, I could observe the block falling and reaching a specific position, at the floor, but it's not really something that I can control that easily. And anyway, it will be, many more steps far with respect to those on the table. So I want to, prioritize things mindfully. And those goals are that far, and very quickly our algorithm understands that, they are far. I have enough certainty that they are far. So EK is small for those goals. And so I stop prioritizing them. And I spend more time in refining things which I'm less certain whether there is an improvement that I can do or not. And now when we check at test time, this means that we can reach much higher success rate, which with many less samples during train time with respect to having, say, just a uniform allocation over goals. So that goal prioritization here is really the key to enable better downstream performance, where you just give me the goal and I have to deliver a policy right away. So this is great, right? So it means that, okay, we have an algorithm that is able to do what we prescribe. So this is working, right? Truth is that now I will, jump to the last part of the talk, where I will reveal that, still there are some failure modes, let's say, for this type of algorithm that suggests why we shouldn't move then to the incrementally controllable notion. Let me pause here just a second and see whether there is any question on this part.
Can I ask a question?
Sure.
What are your state space? Are you working with pixels, images, or what are the states?
We're working with state space. So we're not with the pixel representation, but really with the inner state representation of the robot and of the table and these kind of things. So it's very basic.
So what kind of environment?
So it's really the standard fetch push and pick and place environments with the robotic arm that you have in Visual Code. So it's really basic benchmarks. I think there was another question lined up from Zoom call.
Yes. Oh, sorry.
Hi.
Alessandro, we remove Dico. Yes. I have one question, which is on the exploration side. So, is there any way that so because you're exploring ways to get to a goal, right? Is there any way where the diversity of getting to that goal? So how many ways does my policy express to get to that goal? Is that number embedded in somewhere in those equations that you showed us?
No, at the moment, not really, in the sense that here the focus is really to find the best policy to get there. We don't really try to deliver multiple ways, which can be, interesting for other reasons, maybe for generalization to some extent. Here, we are really prescriptive, saying there is a set of goals which I designed and I don't know, and I want you to find it and find for each of the states in that goal set an epsilon optimal policy for each of those goals.
Okay, thanks.
Okay, so let me go to the failure mode or the tricky things that are happening here. So this is the thing that I went very quickly through, but it's where theory delivers some intuitions and some important messages. So there is something which is very suspicious in this bound here on the number of steps it takes to accomplish that controllable state unsupervised exploration, which is a dependency on S. So the dependency of L is what we expect, right? So the farther the states that I want you to reach, the harder will be the problem. Makes sense. The more the actions, okay, the more things I need to try. The more stringent the accuracy, so the smaller the epsilon, the more symbols I need. All of these things, it's something that we can expect. But then there is a dependency on total number of states. This S is not the cardinality of the controllable states. And this is a worst case analysis, where it's coming from. And it's really coming from the noisy TV type of effect. So imagine that I have, the red goal up there. There is a way to reach that goal deterministically in 2 steps. Take action up, and then in each of the specific random states that I come across, there is a specific deterministic action that leads to the red goal. So no matter what happens, in 2 steps, I'm going to get there. So it's 2-step controllable, easy. But in order to learn how to get there, it's a mess in the sense that for each of these intermediate states, I need to learn what is the right action to do. And funnily enough, all these, more bluish kind of cyan states themselves, they're not controllable because they're, this noisy TV type of thing. So I might have states which are very controllable, go from home to office, but along the way, I might kind of observe a lot of things that I cannot control that confidently. When the bus exactly arrives, when, whether it's raining or not, and so on and so forth. And I have to react to each of these conditions. If the bus is late, maybe I have to take the metro or walk. And so I have to learn how to react to any of these random events. So I need to do that learning. So although reaching the goal, controlling that red state is very easy once I learned it, the learning process to get there can be very, very difficult. So much that I can defend on, in the worst case, on the whole state space. So even if SL is very small, the set of L controllable states is very small, still I might suffer from a lot of other things to learn. And again, this is pretty much the example of the noisy DB. So I'm robust to the fact that I will not stubbornly trying to reach goals that are not controllable. This is good, but I might still suffer from the fact that in order to get to a controllable state, I might cross things that are not really that controllable and suffer from their numerosity or variety. So then we introduce the notion of incrementally controllable states. Let me move to the illustration because the technicalities are a little bit maybe hard to follow, and maybe the illustration it's a little bit easier. So let's talk about the red goal. So according to what I just said, this is controllable in, let's say, 3 steps, but it's not that easily controllable because in order to get there, I have to pass through things that are not controllable themselves.
Alessandro?
Yep.
Just to let you know that if you want to have a few minutes for questions, we should finish now.
Oh, okay. Yeah, I thought that, since we started a little bit late.
Yeah. We're already taking that time.
Okay. So let me, I will take 2 minutes to wrap up, just to introduce this concept and say what is the effect of it. And then I'm happy to take questions in 2 minutes, really. So this red goal here is 3 steps controllable, but as I said, I might need to go through things that are not controllable. Now, let me illustrate another path, which is, going the longer route. And now out of the sudden, this state becomes what we call incrementally controllable in the sense that I can reach it by passing through states that are controllable themselves. And all of these, cyan goals here are controllable because, I can reach them deterministically. Let's say that, that path is very simple and I have specific actions that I can go there. So out of the sudden, I have these, different notions. I can have a state which is controllable, but maybe through paths that are not incrementally controllable because I pass through states that themselves are not controllable. On the other hand, there might be other paths that, or maybe there are not, that lead to the same very goal longer, but through a much better control path, so controllable states. So this is, there is a suitable formal definition of this notion, but it's really, imagine like an inductive definition, like I can define a state as incrementally controllable if I pass through incrementally controllable states, which I reach by passing through incrementally controllable things in an inductive fashion. So why is this now an interesting thing? Well, the reason is that, theory-wise, and really let me just, focus on this object here. We're totally replacing the full sheer complexity of the problem, which is S, right? That big, huge a complexity of life, right? Of the environment by just SL, which is the cardinality, the number of states which are incrementally controllable. So in some sense, I moved from controllable states to incrementally controllable ones. And now the added value of targeting incrementally instead of controllable states is that this is a much more ordered and simpler way of doing things. At the cost that possibly, maybe states that are L controllable, they're not incrementally controllable, or maybe, it takes a much longer L, like in the example, to make them incrementally controllable. So let me wrap up. As I was saying, there are a lot of things to do. Some of these algorithms, again, are kind of extendable to deep reinforcement learning. Some of them are more theoretical in nature. We really need to move to more unified algorithms that are able to scale well beyond, theoretical framework. And more in general, somehow the objective of, this line of research is really towards, having agents that are able to explore autonomously and then being able to solve a downstream efficiently a large set of problems and prompted in very different ways. So happy to talk more about, what are the plans in the lab in that sense, but I will stop here. Thanks a lot for listening and for the questions. Happy to take any other question now.
Can you hear us?
Yeah, now I can hear you. But I can hear a very, very, very low voice in background. I don't know whether it's the question or. I can barely hear anything.
Okay, so in in the incremental setting, how does the specification of the L-step controllable states that you want to explore change? And do you still do the thing where you train multiple policies and then sample for them, or does that no longer work?
Yeah, thanks. So the set changes in the sense that you will be asked no longer to find the L controllable states, but I didn't introduce the notation, but these, sorry, no longer the controllable states, but the incrementally controllable. So now the question that I asked to the agent is somewhat easier, because a little bit like in this illustration, if I just have to focus on incrementally controllable things, then I can expand my knowledge and my expertise much more progressively. And I know that I will not need to learn what to do when I observe a noisy TV in order to reach the red goal. And so the algorithm now is much more careful in its expansion, because it doesn't want to just take any controllable state, but it wants to verify that it's incrementally controllable. So the question is different, is a subset. But the gain of that is that it's much easier. Simple complexity-wise, now I can solve this problem without being lost with sheer dimensionality of the state space, possibly.
Okay, I have another question, which is if the agent is updating its perception as it goes along, for example, learning a CNN, how can it distinguish between it being in like a n-step incrementally controllable thing, or just having updated its representations, but the state space is actually controllable? But it doesn't seem that way.
Great question. So in all this work, I am ignoring representation learning questions, which correctly you point out. So let me give two very quick points. So one is that this example here, you can say that in the bottom trajectory, this is not incrementally controllable for a bad representation. Like, it's a noisy TV. I should just filter out everything that is not controllable, that is noisy, just compress it down, filter it out from my image, and out of the sudden, this red state would become incrementally controllable, because I remove from my perception all the things that are not controllable. So for instance, I could try to use some representation learning step like inverse models and so on and so forth, and it would partially address the problem. There are more subtle cases that would not be addressed by inverse models or trying to do representation learning, but representation learning might play a huge role in bridging a little bit what is controllable, but maybe passing through non-controllable states. And again, maybe this is a fault of representation. And so if I learn a suitable representation, I might take things that are just controllable and make them incrementally controllable, because I would remove details from my input that are not relevant to reach that goal. Just an extra piece, I feel like this might work, but you might need goal-dependent representations, in the sense that, what we, negatively address here as noisy TV, well, those things might be informative and interesting, maybe for going somewhere else. So they're irrelevant if I want to reach the red goal, but maybe they're relevant if I want to do other things. So I think we might need to develop goal-dependent representations here. But again, this is totally open, and I don't have very strong answers to this point.
Great, thanks.
Sure.
the question is like, we have the notion of the controllable states, but for example, in this case with noisy TV, we have like our initial state and we have an action that leads to the like noisy TV state. So does like expression the problem in terms of noisy actions, like like actions that doesn't get us like that are not random help us, because if we can find like actions that are random that doesn't lead to anything, those actions are not really controllable, and it can also help with such a problem.
Right. I would say, the action is still very relevant in the sense that, the right action to move from green to red is go right. So the action is what helps me in going from left to right. And so it's the right thing to do. But I'm puzzled or I'm misled by the outcome of that action, which is locally very random. And it has this next state transition, which is very random, but this doesn't make the action useless. Again, imagine the example that I was giving, going from home to office and going downstairs to catch the bus. It's the right thing to do. But yet the outcome of that action, in the sense, is the bus there, is arriving, it just left, there is strike, it's raining, these kind of things. Well, this is very random. So you don't want to penalize that action for that random outcome. But still, it might be very misleading. And again, the other goal algorithm that I mentioned at the beginning is at least not being trapped in being obsessed by trying to reproduce the exact configuration of the noisy TV, but by goal prioritization, at least it refers to things that are more controllable. And as soon as something is not controllable, it just drops it from the goals of interest. But actions, in some sense, they're doing maybe the right thing, even if their outcome is to some extent random.
Okay, no. So I think it's good moment to